Okay, so last time we talked, basically it was 2 weeks ago, because last week was holiday. So 2 weeks ago we talked about the ethical aspects of metadata analysis. And I hope you looked a little bit into the notebook and in particular the countermeasures you can take in these kind of situations. And today we will be looking a little bit into query optimization. So this is a 2-week block that's not directly motivated by an application. It's more motivated by a problem like, what if the data gets bigger? If you have big data sets to analyze, you have many tables to analyze. So what are the techniques involved in that and what can you do with that? Okay, so that's basically what we had. So we had simple data analysis. We looked at this concrete applications, IMDb, NSA, or similar applications. We learned a couple of things like the fundamental concepts of query processing, like entity relationship modeling, relational model, relational algebra, and SQL. By the way, last week I had a discussion with a guy who is responsible for the schools in Saarland, and we were discussing whether to use UML, Unified Modeling Language, or entity relationship modeling, and I convinced him that please use entity relationship models in school. Why? Because it's so much simpler and easier to read than UML. You can do all of these things. We did an entity relationship modeling with UML as well. That's okay. But when you look at the details, I don't think UML is a very good language for that. You should really stick to entity relationship modeling because it's as simple as it can be. And it's very easy to read, even in particular large models are easy to read. That's just a footnote I wanted to make. Yeah, right. So we looked at these things. Another question we will be looking at is, okay, what if the data gets bigger? How do we actually get from SQL to an efficient program? And that is what's up next. I have new presentation tools here. How does that work? Oh, interesting. Okay, oh, it always stays the same size. Cool. Okay, so and yeah, we looked at SQL, and I already mentioned there are a couple of SQL processing systems, as I would call them for the moment. So, or SQL engines. There are many names for that. Let's call them SQL engines. And yeah, there are a couple of these engines, and they have, differ in their capabilities and in their speed, if you want. Yeah? So there are systems like SQLite. That's a system you frequently run into in practice. It's comparable to a small sailing boat, if you want. And there's a system like MySQL that's very popular when you develop web pages, like database-driven information systems. Then there's PostgreSQL. That's already a pretty old system. However, it's extremely rich in terms of features and asset and all you can ever imagine. It's probably built into Postgres. So I think they started developing in the 90s or something like that. And then there were predecessor systems as well. So it's really insane, the capabilities, the features Postgres has. So for many practical situations, you should be using Postgres to be on the safe side. Yeah? So we're also developing some software at my chair, and there we are also using Postgres because, yeah, that's the easiest choice. And then there are modern database systems, which are sometimes completely insane in their performance features. Yeah? If you want to fly through a wormhole or through a black hole, you can do that with a modern database system. Yeah, you can question whether you need this kind of performance in your daily life just to get to the supermarket. Maybe you don't need a system like that. But I'm just saying, so many insane performance problems are already solved, and you can use fancy systems for that if you want. Okay, right. So the question is, how do we actually get from SQL to an executable program in principle? Yeah, that's what we will be looking at. So I said there's SQL, you declare it somewhere, you write it down, and the system does all of the magic. You don't have to worry about that anymore. Yeah, that's what we looked at. How do I even get to the next page here without switching off the pointer? Doesn't work. Okay, whatever. And yeah, what these systems do, these SQL engines, is what we call automatic query optimization. So there's an entire long pipeline of steps that are taken. So you are just entering your SQL command, and then that walks through a pipeline in like very short time, and then eventually executable code is produced. Yeah? The system will execute that code. that produces the result to the query you specified in the first place. And everything that happens in between, you don't have to be aware about that, yeah? In most situations. However, as you want to become computer scientists or some computer science scientist, DSAI, business informatics, whatever, you should know a little bit about these things, because these things can also go wrong. And then you should really understand what's going on in the system. Yeah, the important thing is all of these optimizations run internally. You don't have to worry about that. And again, depending on the query optimizer, depending on that data system, this SQL processing engine, some of these translation steps can be very simple, with simple heuristics, or even without what we call cost-based optimization. So typically this field of query optimization is divided into two steps. That's the step 2, that is step 3. This is also called heuristic optimization or logical optimization. And then there's cost-based optimization. Now here's heuristic optimization, and then it's cost-based optimization. So typically those are two classes of optimizers. And we will be looking this week at this heuristic optimization, or rule-based optimization, as it is sometimes called. Okay, so the first thing we need is what is called this canonical translation. And we touched upon that already in previous classes. So basically, when you have a SQL statement like this, you can transform that, you can translate that into a relational algebra expression. And again, read it declaratively, so don't worry about performance here. Basically, you know that whatever is in the from clause, all of those relations, that's a big cross product at the bottom of this expression. Then come the where clauses, that's this one. Then comes the group by, that's this one. Then comes the having, this one. Then comes the projection, that's this one. Yeah? That's a very straightforward way of translating a SQL statement into a relational algebra expression. Further steps you can do is you should handle views. We talked about that in that SQL notebook. Yeah? You can define views, and then they are basically just text replaced into the plan, but it makes your SQL statements much more readable. You can also do like straightforward optimizations like partial expressions. So if you already computed part of that plan, part of that relational algebra expression before, you can just use a cached result. Yeah? You had a very similar query, or even the same query before. Why do you even re-execute it? You can just return the cached result, which is a good idea if the data didn't change in between. Yeah? But if you can find out about that, just return the cached result, or what we call in databases the pre-materialized result. Yeah? Materialized in databases means it was really written somewhere on some storage medium, yeah? Either on hard disk, SSD, or in main memory, or in any cache. The data, or the query result in this case, actually was written there. Yeah. Here's a very straightforward example. Exactly the same query has already been calculated, and the database has not changed. Return the cached result without re-executing the query. Yeah, but that should be done automatically. You shouldn't have to worry about that. Ah, 2 fingers. Now I got it. Okay, and there's this typical what versus how confusion in databases, and here it's also with respect to relational algebra. So relational algebra can be read declaratively and procedurally, which means declarative. What is the result? Yeah, that's what I used before. You write that relational algebra expression. It doesn't matter in which order you specify those operators, as long as the result doesn't change, as long as the semantics of the query doesn't change. So the order of the operators doesn't matter for certain situations. For instance, the order of 2 selections is completely irrelevant for the correctness. Right? Whether you first filter on A and then on B, or first on B and then on A, doesn't matter for the result of the query. In addition to that, we also do not care about how those operators are implemented. So for instance, we do not care how a join is implemented, how a selection is implemented. We are purely on this abstract logical level where we ignore the algorithms. And this is what we did so far. Yeah? So we ignored order, and we didn't care about implementations. And now we look a little bit more into the details in terms of a procedural reading of relational algebra, because we can we could say, oh, the order actually matters. Yeah. Now we want to execute relational algebra operators in exactly the order specified, and we can also worry about how those operators are implemented. Questions? Question? We can also worry about how these operators are implemented in the first place. And that's a procedural way of reading that we will apply in the following. Okay. It's actually pretty cool, these new tools. Okay. So, and we distinguish that into logical and physical operators. So when I introduced relational model and operators, there I said relational algebra only abstractly describes what has to be calculated, but not how this calculation is implemented algorithmically. And actually, we ran into the problem in this notebook, Relational Algebra, where when specifying those operators, there was always this selection underscore and then the implementation, like scan, selection underscore scan, whatever, join underscore simple hash join or something like that, because in order to implement an operator, when you have to specify an algorithm, there's no way around that. Yeah? So there already you saw this physical aspects of an operator. So basically what that leads to is a one-to-n relationship between logical and physical operators. So logical is just the Greek letter or some relational algebra operator expression, and that can be translated into several physical implementations. Yeah, for instance, a join can be implemented by first running a nested loop, so basically a cross product. Each tuple from the left input is combined with the tuple from the right input, followed by filtering. Yeah? So only for those tuples that qualify under the join condition, a result is returned. Yeah? That's okay, you can do that. That has square complexity, not very efficient, but that gives you the correct result. And then there are many more other much better algorithms that use indexes, that use partitioning, that use co-grouping, blah, 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 blah. There are many, many decisions that can be taken. And again, all of these decisions are taken automatically. You don't have to worry about these things. That's a cool thing in databases. Who cares? The database will figure out what is the best implementation of your logical operator. And the same holds for all operators. Yeah, so for instance, intersection operator, you can do that nested loops based, which is not efficient, or index based, and so forth and so forth. Or a very important expression in a plan you will be seeing very often is a base relation like R, and then on top of that there's a selection operator. And of course you can simply read all of the tuples from R, and then for each tuple you check whether it qualifies under that predicate. Yeah, then you have linear costs, or you have some sort of data structure that allows you to only get the tuples that qualify under your condition. Yeah? A data structure allowing you to directly access the qualifying tuples. These data structures are called indexes in databases, and we will be looking a little bit at that today. Yeah, so there are many decisions you can take here. So in the following, I will need a couple of need some terminology. And one is the term plan. What is a plan? So we should have a plan in life, but also in databases. So plan is any valid relational algebra expression consisting of logical and of physical operators. Yeah, any relational algebra expression you saw so far, we consider a plan. Be it that the operators are logical or physical, I don't care, it's called a plan. If such an expression consists only of logical operators, I will be calling it a logical plan. If it consists only of physical operators, I will be calling it a physical plan. Yeah? But there can also be hybrid plans where some of the operators are logical and others are physical. That's okay. And one thing we now need to look at is what is the quality of a plan? So there will be, I mean, you can already see that from here. If you have so many options, it boils down to, you have for the same SQL expression, you will have zillions of different plans, zillions of different possibilities to execute a plan that computes the result to that SQL statement. Yeah, so we have a huge search space, as we are calling it, and you have to have a measure to understand, okay, that's a good plan, that's a bad plan. How do you decide that? You have to have an understanding of that. So we have to have a notion of the quality of a plan. Yeah? So and for that we need to develop a function that can compute or estimate that quality. And it's important to understand that quality doesn't necessarily have to be runtime. Yeah, maybe you're optimizing for, I want to have the fastest plan. Yeah, maybe that's your optimization goal. So low runtime, it's a typical thing we do. But it could also be low power consumption. And that doesn't necessarily have to be the same as low runtime. Yeah? You are running on some small device, some embedded system, whatever, and you really want to make sure that you don't waste energy. Yeah, so low power consumption will be your optimization goal. Or it could be that you're operating on a bad network. Yeah, so you really want to make sure that you don't load much data from the network or don't send data over the network. That could be your optimization goal for the plan. Yeah? Depends on the situation. Yeah? So quality may be defined in many different ways. Yeah? And for that we need some other terminology. Yeah? So here, the first couple of slides today is really a lot of terminology we will be using throughout the rest of the lecture because it's so fundamental. Yeah, and one important term is selectivity. This is for the moment defined on a unary operator. So an operator taking one input relation and creating one output relation. R gets in, R prime gets out. And we say the selectivity is the ratio of the size of its output relation R prime to its input relation R. Yeah, so I'm using again this, if I make it bigger, it gets bigger here as well. Oh, yeah, that's really cool. Okay, so that is the input relation, the number of tuples that are contained in that, no, sorry, that's the output relation, of course, that's the output relation. You have the number of tuples contained in the output relation, and here we have the number of tuples contained in the input relation. Well, this can only be smaller, so this is smaller equal 1. So for the operators we learned about. Yeah? So you could also have operators that like output 3 tuples for every input tuple or stuff like that. We didn't have that. But for a typical selection operator, for instance, filter operator, you will have something like this. Yeah? So you can only get a subset of the tuples that are input to the operator, and therefore the selectivity will be smaller equal 1. And yeah, there's a problem with naming of selectivity. So often there's a confusion here with selectivity, and that is high selectivity versus low selectivity. So if you look at an example where we have an input relation R with 1 million tuples, and then we have a selection on predicate P that returns 1,000 tuples, and another selection with predicate Q that would return on the input R 500,000 tuples, then we can do the math for P, for instance, yeah, be something like that. So whatever the number of tuples returned by that selection, so that's 1,000 divided by 1 million, that's 0.001 or 0.1% of the input relation is returned. In other words, many tuples are filtered out, many tuples are discarded, only few tuples are passed on to the output. And interestingly, we are calling that a high selectivity. If this number is low, this is highly selective. Yeah, there you have to be really careful with the naming. If someone says it's highly selective, that means only few tuples are sent to the output. And the other way around is low selectivity. Few tuples are filtered out, so you hear only half of the tuples are discarded. Most of the tuples, the other half of tuples is as part of the output. Yeah? And that is called low selectivity, where low starts and high, where low ends and high starts. It's in the eye of the user. Yeah? So typically high selectivity is something like, okay, at least 1%, yeah? Or even more selective, like this one, is 1 out of 1,000 tuples are selected. Yeah? That's a very important term. Yeah, and then if you, even this is the easiest thing you can think about in query optimization. Now we have these two selections. It's also a problem that's present in compiler construction. So again, we have the same example here. And then if you want to execute both of these selections, yeah, and then you have the option, okay, I first execute this selection on predicate Q and then on P. and here it's the other way around. First P and then Q. Yeah? So Q first filters 1 million tuples to 500,000 output tuples, and then P filters 500,000 input tuples. And then you can do the math and say, okay, how many tuples do I actually inspect in this kind of computation? Yeah, so in this situation, here you inspect the 1 million input tuples and create another 500,000 input tuples. That gives you 1 million inspections, if you want. Yeah? And then those 500,000 tuples created here are again inspected in this selection. That gives you another 500,000 inspections, and therefore you get 1.5 million tuples you're inspecting in this kind of execution. If you do it the other way around, so again you will be inspecting 1 million tuples in this inner predicate P, that will create 1,000 output tuples, but that means that this outer selection on Q will only have to inspect 1,000 input tuples. Yeah? So you only in total inspect 1,001,000 output tuples. And that already could lead to some sort of quality measure. You could say, hey, maybe I organize the order of my selection predicates in a way that I minimize the number of tuples being inspected. In other words, you first look at the predicates that are highly selective, that remove a lot of tuples. Yeah? Basically, you can sort your predicates by their selectiveness. Highest selectivity first, then the second highest, third highest, and so forth and so forth. Yeah? And then you can optimize on the number of tuples being inspected. Right. So to get that a little bit more formal, it's not very formal, but a little bit, we need to define a cost model. And what is a cost model? That is just a function that estimates the execution costs or any other quality measure for a given partial plan using a suitable model. Yeah, so for any plan P, we define a function that when given that plan to that cost function returns some float, sometimes also an integer, it doesn't matter, some number. Yeah? And we will interpret this as a quality of the plan. So note here that this doesn't have to have a unit. It doesn't have to be milliseconds. It doesn't have to be joule if you're optimizing on energy. It's just a number. And the only thing you want to make sure is that if for one plan the number is smaller, yeah, then you interpret this as, oh yeah, the quality is better. That is a better plan to look at for me. Yeah? So higher means worse and smaller means better. And that's exactly what we can use for the example above. Yeah? In this selectivity example, we argued that the evaluation order is better of this plan is better because fewer tuples need to be inspected during execution. So we could phrase that into a cost model on the number of intermediate results. So this cost model, so I will define multiple of those cost models in the moment, on other slides, but for the moment, that's the cost model on intermediate results, says, okay, the costs of a plan is the sum over the cardinalities of the output relations of all operators in P. Yeah, so whatever intermediate results are produced in a plan, I just sum those things up. And one important thing to note here, in such a cost model, I'm ignoring the size of the inputs. Yeah, if you go back to this plan, you will see that in both of those calculations, I factored in the 1 million results from the input relation, right? That doesn't make any sense because it will be used in both of the plans. It's just adding up the stuff. I mean, it's 1 million I'm adding in all of those options. It doesn't help me to make a meaningful decision, so I could directly leave it away. Yeah, so in this cost model, I discard the sizes of the inputs. I'm only looking at the intermediate results. So that would mean that I would get 500,000 here and 1,000 here, making a huge difference in that plan. Okay, right. Yeah, important here is also what I wrote down here for your reference. So this is a model. Yeah? And model means I leave some things away. So I just try to focus on the most important features that determine the costs I'm interested in. So in particular, what I left away here is the runtime. Now, what is the runtime of a join or any operator? Or the access to certain relations. How long does it take to get the stuff from disk, from network or SSD? All of this is ignored in the model. Yeah, and that's something you should really be aware of. And so we are using these models in this lecture and in other lectures, and the model is a way of abstracting things away. And you always have to be careful to compare your model back to reality. Does the model really reflect what I'm trying to express here or not? Yeah? So there will be more complex models that will factor other things in. Yeah? And examples for that are on this slide. So here's a collection of other important models. I/O, for instance, so input-output operations, and comes in various flavors. But basically, you could just say, hey, my cost model is just the sum over all access times, read times, write times from hard disk, SSD, network over all input relations. So basically, whenever you touch storage, whenever you read something from disk, from SSD, or write something, you just count that into your cost models. And that is the estimate for your plan. So when does that plan make sense? If you want to optimize queries in a database, you want to find out what is the best plan in terms of runtime. Yeah? And now I'm telling you, okay, in order to find out what is the best plan, and where best means the fastest, I will be using this cost model. In which situation exactly is this a good idea? Yeah?
Whenever you are bound by this, basically, by this vector?
Yes, correct. Perfect, perfect answer. So whenever I'm bound by disk, when the bottleneck is the I/O, yeah, then this is a good cost model. If my bottleneck is the CPU and I'm just counting I/O operations, that's not a good model, because then I should be rather modeling the CPU costs. Yeah? But for many older database systems, so when people start developing stuff in the 80s and the 90s, that was the only cost model people were interested in. They completely ignored CPU costs. Yeah? I mean, there were situations, of course, whenever you started doing some nested loop style, squarish complexity thing, I mean, then you would forget it. Yeah? Then you would be running into CPU problems. But at those times, you had so little main memory, and the disks were so insanely slow that was all you ever needed to model. That's all you ever needed to grade, to come up with the quality of a plan. Yeah? And that changed when systems moved more and more into main memory systems. Yeah, that's another cost model you could come up with. So what's the problem with this cost model? Anyone has an idea? Yeah, someone else? So the total runtime of a plan I'll be using as a cost model. Why is that a good idea? Why is that a bad idea? Yeah?
Well, first of all, it's not a thing that exists independently of the system you implement your state in. So it's
Yeah.
hard to measure that globally.
Yeah? It's independent from the system, you mean? It's not independent from the system. Yes, that's true. Yeah? How do I come up with the runtime of a plan, of such a plan in the first place?
You have to do it anyway. So
Yeah.
you have to execute, and at this point, it's making up certain functions.
Right, you have to execute that plan to come up with a runtime. We will be looking at a world where we are pondering upon the options. Yeah? We're looking at all of these different plan options, but I don't want to execute all of these plans. I just want to execute the best plan without executing it before to determine what is best. Yeah? Of course, you could, if you have 100 plans, you can first execute all of these 100 plans and then take the one that has a minimal runtime cost. That is okay, but then you executed 100 plans, right? I mean, that's not so smart, right? So you only want to execute one plan and the others, right, yeah, the access, right, in the end, and so basically use a cost model to make an estimate, yeah, without executing the actual plan. Yeah, energy consumption, that's another one. Here you could, it's the same problem as here. You can measure the energy, but then you need a predictor. You need to have a good energy, a more complex model to make a prediction on that. And the other is main memory. So the amount of main memory required to be able to execute the plan. Again, you could measure that, but there are many ways to predict the amount of main memory and make meaningful decisions here. Okay. So we will be looking at heuristic optimization here. And the basic idea is, so for the moment we discard the cost models. So heuristic optimization, the idea is as described here. So you iteratively transform this canonical plan. So you did the canonical translation to this cross-product expression. And then we want to iteratively transform that plan into a better plan. And this will happen rule-based. Important is you never change the outcome of the plan, so the semantics of the plan mustn't be changed. Of course, you always want to produce the same result. And we will attempt transforming the plan until none of the heuristic rules are applicable anymore. And this is heuristic also in the sense that the rules we will be applying always reduce the costs under a given cost model. So we have a cost model in mind, however, we don't feed the plans we generate in that process into those cost models. That's an important distinction we will be dropping later on, but for the moment we don't need the cost model actually to make that happen. And that's the algorithm. It's as complicated as that. It's 2 lines of code. So basically you have a plan and you initialize it with a canonical plan in the beginning. You have a set of rules. And then you see whether any of those rules matches the plan. And if that is the case, you rewrite the original plan into a new plan. And then you keep on iterating until you get to an end. And maybe I will just show the next slide first. So basically, so what is a rule? A rule is defined on such an operator tree or plan, as we call it. And it's basically a predicate telling me whether a specific expression that is encoded in that rule matches. So that is a search method that checks whether the input tree operator matches a certain substructure or a certain pattern. For example, the match could be, is there a selection with a conjunction in the predicate? That could be the thing. There's an A and B, for instance, in that in the predicate of a selection. That could be the single match operation. Or is there a selection with the joint predicate directly above a cross product? That might be indicating to something like you could rewrite to a join later on. But that's the check you're doing. So if the match returns true, the match part of the rule, you can run modify. Modify means you create a new operator tree. So you transform the input operator tree to an output operator tree. So in our examples, so you found there's a selection with a conjunction in the predicate. Well, modify the tree. Break up that predicate or replace a selection with 2 separate selections. Before you had one selection operator, A and B. Now you have selection on A followed by selection on B, or the other way around. Doesn't matter. It's the same thing. Or in this situation, if you found this match, you could say, okay, I get rid of the cross product. I combine that selection and cross product into a join. So you rewrite the cross product plus predicate, fuse those operators into a single operator that is a join. And now we will be looking at, here some more details on, we can ignore that for the moment. So to make that algorithm work, you have to, you can do many things. You can cap the number of iterations. You should limit the number of, limit the effort you use for optimization. You should prevent oscillation. So oscillation meaning if you have a selection A, so first select on A and then on B, you can always swap these 2 selections because it's the same thing. And if you have a rule that just swaps these 2 selections forever, you will never terminate in your algorithm. So these tricks you have to do. And you could also include priority of rules. So if you have a large rule set, you can always try to prioritize certain rules. Something like first, you always try to apply rule 42, and if that doesn't match, only then you go to rule 4. And it could also be that certain rules only work after a certain rule was applied. So only when 42 was applied, then rule 4 may even match on the plan. All of these dependencies exist in these kind of optimizations. Yeah, so let's look at some of the transformation rules, and then I will be showing that to you also in a notebook. Predicate pushdown. That is the mother of all transformation rules, actually. It occurs all over the place in computer science. So we have two relations, R1 and R2. We have P, that is a predicate, and this expression is all the attributes being mentioned in P. Yeah? So the attributes on which P imposes a condition on. Then we can formulate the following optimization rule. So if we have an operation, a binary operator on R1 and R2 that is either a join operation or a cross product, followed by a selection with predicate P, and the attributes of P are all contained in the schema of R2. So in other words, you have a condition in the predicate, for instance, A equals 42, yeah, where A is an attribute of R2. Yeah? In this situation, we can push down the predicate. So basically now I push down this selection predicate into, before the binary operator kicks in. So I first filter on R2 here, and whatever the output is, then goes into that binary operator. Okay? So the selection should be pushed down as close as possible to the data sources. And here I have a selection, I have a binary operator, and I'm pushing that selection through the binary operator down to R2, on top of R2. Okay? So why is it a good idea in almost all situations? Yeah, someone else? Yeah, red t-shirt, yeah. Right, yeah. Minimizing the number of tuples that go into the join or cross product. I don't change the complexity of the join or the cross products, but the size of the inputs change, and with that I most likely change the runtimes of those operations. That's a good idea to reduce the input sizes of these operators. Yeah? Okay. And yeah, the examples of predicate pushdown I denoted here. That's another example of a technique that occurs all over the place under different names. So the first thing I put here, actually, I heard about a couple of years back. There was actually a startup in Hamburg doing that. That was their business idea. So there are satellites, they generate those satellites generate all of these huge images, and the idea was, hey, why don't we save network time by not sending down the images first to the base station, to the ground station, and filtering it out? Why not filter it out on the satellite and just send down the interesting stuff down to Earth? That's a predicate pushdown. Yeah, actually it's a predicate push up to space in a way. Yeah, you have to do it the other way around. Yeah. But in terms of technology, it's a predicate pushdown. Yeah? So avoiding network, avoiding that all of the data gets sent down. And it's the most straightforward thing to do. I'm not sure what happened to the startup. It's a super easy technique. Sensor data is the same thing. So here you evaluate filter conditions directly when measuring the data. So for instance, assume whatever temperature sensors in a room or in a machine or something like that. Yeah, they measure the temperature like every second, have a new reading of the temperature, and you could send all of the data to a central place. You could also say, well, no, I will only be sending it if it changes. It could be a very straightforward optimization. Or maybe you run a filter on the sensor saying, oh, just send out the data if it's above 100 degrees Celsius or something like that. Yeah? It's very straightforward. Another example is IMAP, of course. Yeah? You can filter, you can first download all of your emails, filter your emails on your client, or you can filter directly on the server, of course. Yeah? So if you filter on the server, that's predicate pushdown. Then smart disks. that also appears under a zillion different names. So the idea is that the storage medium you're using already has some logic built into it. Normally you use this as a dumb storage medium, and that includes hard disks, SSDs, and DRAM. But what if you could push down those selection predicates to the storage medium? If your disk or SSD were able to pre-select some of the data and only send up the stuff you're interested in. These things exist in a zillion different ways and make a lot of sense in data-intensive systems. So not for daily use, but for data-intensive systems, that's a very good idea to be able to work with large data sets. Yeah, and then in any distributed system, you could do that like you evaluate the filter on the remote system and then send only the filtered results instead of all the data. That's basically a generalization of this IMAP stuff I showed before. So here's a notebook we developed that explains a little bit rule-based optimization. And yeah, we'll be using the IMDb schema that we used before in other notebooks. So here's the data tables again displayed with all the data. And yeah, I think we can directly start here. So that is a query. That's a canonical query. Yeah? So basically, the stuff if you translate SQL to a canonical representation, that's what you end up with. So you have this nasty cross product underneath. You have these two input relations. You have all kinds of selections here. One is an OR condition, disjunctive query, a conjunctive query with an and so forth and so forth. And on top, there's a projection. Yeah? And now we can throw rules at that. Yeah? So again, that's what I showed before. And now I can execute a rule, and that is this break up the selection rule. Yeah? And then we see what happens to the plan. Now here you have 4 selections. Previously, we had this selection here, last name equals Tarantino and probability smaller 0.7. So that can be broken up, and we see it here in this plan. Now it's broken up. And why does that even make sense to break up these selections in the first place? If you think about something like that. Why would I break up conjunctions in such a query? Yeah, someone else? Why could that be a good idea? Yeah, red T-shirt again? Yeah. Yeah, okay, that's okay. So the order thing, but that also applies if you have the conjunct. Yeah, however you translate that in a programming language, you can still order the conjunctive expression inside and make a decision on. Yeah, so you don't have to fully evaluate those end expressions in the programming language. You can say if it's false already on the left input, you don't have to look at the right one. So it's the same thing, just inside the language. Yeah, that's all okay. But if you think about that as an enabling rewrite for certain things, why could that be a good idea? Yeah?
I think last name is selection on directors and prop is selection on directors genre.
Yeah, I don't even know whether prop is director genre. Yes, yeah. And that means what exactly if you break it up? Well, yes, you can push it down individually. So one part of the expression goes to the left and one part of the expression goes to the right. That's not possible if it's still baked into one expression. So that's an enabling rewrite for selection pushdown. Very good. Yeah, now I actually push down the selections. Again, that's the before and that is the after. And there you see what happens. Yeah? So the probability, that's exactly what you said, yeah? Goes to director genres, last name to Tarantino. There's another one that can be executed here, so you can't break this thing up because that's this OR condition, but as genre and prop are both attributes of director genres, you do it here. yeah, then only those filtered results go into the cross product, not changing the complexity of the cross product, but having much smaller inputs, probably making this a better plan. Yeah, that is a kind of rewrites we looked at so far. Okay, so with that, we look at a couple of more rewrites that are possible in such a system, and one is projection pushdown. So let R be in relation, P a predicate, and again, these are all the attributes that are referenced in P. Then we can formulate the following optimization rules. So if you have a selection with a predicate P on R, followed by a projection on that schema A, and we know that all the attributes that are referred in P are all contained in that schema A, we can push down the projection towards, into this expression, like here. Yeah? So you first do the projection and then you do the selection here. Yeah? And the second is basically a variant. So here you say, okay, I'm in a similar situation as here, that's the same thing. However, I'm not in the situation that all of this stuff is contained in A. Yeah? I mean, A is a subset of R, of course, but not all of those are contained. So then you can still enrich this schema. You can say, okay, I will add the missing attributes. So the attributes that are referred in predicate B, we'll be calling that the B schema. And then you do the same rewrite, however, with an enriched schema B. So B is schema A plus all the predicates that are referred to here in that selection. That's a rewrite you could do. Yeah? And yeah, why would I do that? Why would I do that? Yeah?
In a simple case, it's really helpful because you decrease dimension of your data before you do your select. So essentially, you're dividing the times of the tuples you have to inspect.
What do you mean by dimension?
Just fewer attributes.
Yeah, few attributes. It makes the relation narrower. Yeah. So if I have a relation like that before, and I'm only interested in 3 tuples, in 3 attributes, then you can do something like that, and it will lead to pushing less data through the pipeline with high likelihood, making it more efficient. Also, when you have cost models like main memory that you spend in the pipeline. Okay. So projection should be pushed down as close as possible to the data sources. So here's an example on the slides. Don't confuse the two things, projection pushdown and predicate pushdown, 2 different things. I have a sample schema here. I have this expression here, doing a join, foreign key join, and then projecting on A, C. A is in the red, it's in the R input, C is in the S input. And then what I do is I push down projections. So here there's no projection, no projection. Now I add a projection here and add a projection there. And yeah, I'm extending it by that ID attribute, which is used in the in this join condition here later on. That's very important. So this is executed first, that is executed first, and then the results are fed into the join operator. In order to be able to evaluate that condition, I need the ID, I need the R_ID, and therefore I have to, I can push down the projection, but I have to make the schema a little wider, depending on what I'm using above in the plan. So I add additional projections. So there you have to be a little bit careful when doing that. Another very important transformation rule is projection pushdown through a join. I think we kind of saw it before in the example, but again here in a more formal way. So we have a join here on these 2 input relations R1 and R2 with join predicate P. Here's a projection. No, before we saw, no, I'm confusing selection and projection pushdown. So we saw selection pushdown, now we're looking at projection pushdown. Right. So, yeah, under certain conditions, like that the schema of A, so that is the attributes you're projecting to, is contained in the concatenated schema of both input relations R1 and R2. then you can again create an extended schema B here, and then you can add a projection like that. Push down the projection, here in this case only to one of the inputs, that is fine. You can also do it for the other input. Yes? So the general rule is you can push down those projections as long as no attributes of the joint predicate are lost. You have to make sure that the predicates still exist, otherwise you wouldn't be able to execute the join later on. Yeah, conjunctions can be broken up, we said that. So what else should I? Yeah, that is a rule I can show in the notebook in a moment. So that is a rule saying, okay, we have this situation in a plan, so a cross product followed by a selection predicate, and we know that the attributes being mentioned in that predicate, at least one of the attributes occurs in R1, in the schema of R1, and at least one of the attributes occurs in the schema of R2. So that's a classical joint predicate, yeah? A equals B, where A is part of R1 and B is part of R2. So that we have a joint predicate, that's basically what these conditions are saying. Then we can rewrite this expression to a join, yeah? where P becomes a predicate of that join expression. And that's an important rule because later on, when we translate this can be translated into something that's way more efficient than square complexity. This is whatever you do is square complexity. No way around that. But this can be done in linear or n-log n time easily. And that's why it's important to be able to do these transformations in this, at this point in time. Yeah, we do that in the notebook. So we ended up with this plan. We have a cross product. We are exactly in this situation that there's this ID equals director underscore ID. So that's the foreign key condition. And now I want to rewrite this stuff into a join. Yeah? And we have a rule for that in our implementation that does exactly that. So again, that is where we start and that is where we end. And now we got rid of the cross product and we replaced it by a join operator. Here's the other, the final thing I showed before. So we can insert projections all over the place. And that's what you see here. Often we leave this stuff away. Yeah, we know that we can insert projections all over the place, but very often when you see those plans, these things are not denoted because they really blow up the plan and then makes it hard to read. But even if you don't specify those projections on the plan, in typical implementations, you will be doing these kind of things. Yeah? But you leave it away because you want to have readability here. And you see it here, basically. Yeah, here you can, for instance, project to probability and director underscore ID. You don't need genre anymore. Yeah? So previously, you needed genre to be able to evaluate this selection. But that only happens here, and it's not used in the final projection. So this genre condition is only used here. So once you evaluated that expression, you can directly project to whatever comes above. Yeah? Above, you only have director ID and probability, so you can already discard all of the attributes that are not mentioned above. Yeah? Those are those projection pushdowns. Okay. I have a couple of more rules here for, yeah, I don't think we have to go through all of that. That's basically what we had in the initial example. You can interchange those selections, doesn't make a difference, yeah? But if you look at costs, it makes a difference, but in terms of correctness, it does not make a difference. So important, again, for all of these rules is they must change the semantics of a query. Yeah? So that's important for all of these rules, and all of these rules fulfill that. You can actually prove that yeah, you can apply these rules and the semantics of the query will not change. That's very important. If you change the semantics, well, then you're in trouble. Okay, so with that, let's look a little bit at what I promised you before, look a little bit at indexing. Indexing is a database term for data structures, and for that I have to remind, some of you have to remind you, some of you see that for the first time. If you study data science and AI, you see this slide actually in the first semester. So we already talked about non-recursive induced horizontal partitioning. When we talked on IMDb, basically what I want to have is I want to define a set of partitioning functions that somehow map from the schema of a relation to some appropriate output domain. And now what I want to do is I apply all of these partitioning functions to that input relation R, and that results in a set of horizontal partitions. Yeah, and I do that recursively. So maybe let's start with the example here. So I have that input relation R with only 4 tuples, and I have 2 partitioning functions. Yeah? That is my first partitioning function, basically just returning whether attribute value A is odd or even, modulo 2, it returns 0 or 1. And the second partitioning function, just returning that character, yeah, this B attribute of tuple T. We used the same when we talked about IMDb. And now what I'm doing is I first apply one partitioning function and then apply the other partitioning function. The order doesn't matter, the end result will be the same. But basically now this is saying, okay, this is a horizontal partition that contains the tuples when fed into P0 will return 0, and when fed into P1 will return A. So the 0.A partition, if you wish. Yeah? And that's only this tuple. Yeah? So it's an even number, and the B value is a capital A. And you do that for all of the data, and here, of course, you only get the partitions that actually contain some data. You might, in theory, have many empty partitions, but they're not displayed. So this is again even and C, odd and B, those 2 tuples. Yeah, that's the recursive horizontal partitioning that you can define by using appropriate partitioning functions, however you want to define those. Well, and with that, we can directly start with the definition of an index. So what is an index? Any set of recursive or non-recursive horizontal partitioning functions that can be used by a query to reduce the query's search space is called an index. So typically the search space of the query is the entire relation. Yeah, if you just think about a single relation, yeah, you want to filter out the tuples qualifying a certain condition. So the search space is all of the tuples. However, using horizontal partitioning, I can just look at some of the horizontal partitions and not at all of them. Yeah, that's a trick that's played by indexes. Yeah? So the goal of the index is to reduce the set of horizontal partitions we have to inspect to compute the results for a query. Again, the same example. So we have this horizontal partitioning, this recursive induced horizontal partitioning. And now if you have queries like shown underneath here, like shown here. So for instance, you have a query querying for all tuples where the B attribute equals C, then you can rewrite that to this query here, yeah, that doesn't operate on R, but on R 0.C. Yeah, because you know tuples can only, the tuples qualifying can only exist in this relation. So you're only expecting 1 tuple instead of 4 tuples. Yeah, so basically you're rewriting the input queries. Yeah, here's the same. You're filtering on A equals 7. Well, I only have to look at those horizontal partitions that contain the odd numbers. Yeah, the even numbers cannot qualify. You only have one partition that has odd numbers, so you simply rewrite it to R1, B. It returns the same result. Yeah? It's much more efficient. The same for this one. You know, oh yeah, that's even number, so I basically could do something like that. I just inspect those 2 partitions, and then you filter only on 2 tuples instead of 4. Yeah? Yeah? It doesn't mean that, of course, so be careful, you cannot simply return the contents here of those partitions. You still have to, as we call it, post-filter the result. Yeah? But you know the input you're operating on is much smaller than if you were operating on the original input R. Yeah? That's a trick that's played by any data structure and by any index. It's a high level, the concept of an index or almost all data structures. Yeah? Yeah, and in some more detail, so the two types of queries we are differentiating in databases are point queries and range queries. So point query is an expression like this. Yeah? So you have an attribute name on the left here, and then there's some sort of constant, yeah, like a equals 42 or something like that. That is called a point query. A range query is something like that, and basically you have a condition like, okay, my constant is contained in some interval, from low to high including, or you write it like that, yeah, C is greater equal low and smaller equal high. Now that's the same thing. That's called a range query. You're interested in a range of values. And then in a database system, or in a SQL engine as we are calling it for the moment, you have multiple options to execute these point and range queries. And those are the three most important ones, but I would also say, I mean, you are fine if you understand the first two. So hash tables are suitable for point queries. You have a direct lookup into the hash table, into some bucket in the hash table, and then whatever hash table you're using. Point queries are very efficient in the hash table, typically constant time, something like that, depending on the implementation. Yeah? So point queries, that's important to understand. If you have point queries, hash tables are great, although there are special variants for range queries. Yeah? They do exist, these variants, so it doesn't mean that you cannot, there's no way of teaching a hash table to do range queries. There are tricks you can play, but in the general case, hash table is good for point queries. B-trees is the most important index structure in databases. I will explain it in a moment. So that's a tree-structured index, which is both suitable for both point and range queries. And I will show you in a moment how. And then there's a third class of structures that's called bitmaps. That's more advanced stuff you don't need in the moment, but with that you can also play many tricks, including for point queries and even for range queries. So let's look a little bit at B-trees. So assume that you learned about hash tables, and I also learned that you looked at probing hash tables in programming 2, right? Yeah? Okay, very good. Yeah, so you don't have so typically the first, how hash tables are explained, yeah, you have these buckets, each bucket has an overflow chain, and that's a hash table. Yeah? But there are also hash tables that only have that array, that hash array in the middle, and if a bucket is occupied, they keep on searching somehow in the bucket for a new place. And there are many ways how to do that. Cuckoo hashing, Robin Hood hashing, quadratic exploration, blah, blah, blah. Those hash tables are typically the better choice than a hash table with overflow chains. One could do half of a lecture with hash tables, maybe an entire lecture. That's many variants exist. Okay, but so let's look at B-trees. So what is a B-tree? So a B-tree is a variant of an n-ary index structure that is very suitable for databases, as it can be super easily mapped to storage. Yeah? That is the motivation for that. It was proposed in 1972 already, so it's really a classical structure. And the cool thing about that is you can adapt it and change it for all kinds of problems. Yeah? So the rule in databases is really, if you have an indexing problem, did you try a B-tree? Yeah? So there are people that invent new index structures, but it turns out in most situations you can somehow map the problem to a B-tree. Yeah? Again, laziness principle. Yeah? So maybe you can adapt the B-tree in a way that it works for your specific problem. Yeah? And basically it only has two different types of structures. One is internal nodes and the other is leaf nodes. So internal node is something like this. Yeah? So you have a couple of outgoing pointers. Basically, you have n keys, here n equals 2, and that implies that you have n plus 1, so this is 3 outgoing pointers in this structure. And then there's leaves. A leaf contains key value pair entries. So here's again the keys in sorted order, and for each key you have an entry which is a value. So it could be whatever. It could be a tuple, could be a pointer to a tuple, could be a character, could be another number, whatever you want. So that's the main idea. And we will need to differentiate whether a node or a leaf is what we call the root. Root is the topmost structure of the tree, like in standard binary search trees. They have the root node on top. Yeah, with the top node or leaf in the B tree is also called the root here. And for root, we have extra rules that they can do certain things. The important thing is, are these rules here? So if you look at these, those are very similar rules for both nodes and leaves. Basically, what these rules say, yeah, whatever you do, the node at all times is at least half full. So half of the node is occupied with entries. That's basically what this is saying. Yeah? So the number of keys in that node is in the range from k to 2 times k. Yeah, that is the rule, half full, unless it's the root. If it's the root, it could also be that there's only one key entry. That is fine for the root, but not for all other nodes. And the same occurs for leaves. So here we have a k star parameter saying it's the number of key value pairs in such a leaf, here k star equals 2, is in between k star and 2 times k star. So here in the range from 2 to 4 in this example, unless it's the root, yeah? Then it's completely fine that there's only one entry. So the smallest B tree you can think of is a single leaf with only one entry. That's okay. That's a valid B tree. Okay. Yeah, these parameters k and k star can be defined freely. Yeah, however, they are, in practical implementations, they are implicitly given by the maximum size of the node or leaf in bytes. So what that means is, typically, in a storage system, in particular in an older storage system on operating systems, you have what's called a page. That's a chunk of data, like 4K of bytes. And what you do with B trees is you say, oh, I have a 4K page, and I will use that for a node or a leaf. So you say each node will be mapped to one page. A page contains only one node or one leaf. And then with that, those structures become very, very easy to handle in a storage system. That's just a side note. So let's look at an example. So here's an example B tree with some made up numbers. Yeah, it's so impressive you really throw everything away, right? Okay. Okay, so this is a made up B tree, and here I have k1, k equals 1 and k star equals 2. Yeah, so here the nodes have 1 or 2 key entries, and the leaves have 2 to 4 entries. Yeah, and then if you look at how can you run a query like that, it's very similar to a binary search tree. So basically, if you do a point query, you will see that you start with a root, and now what the algorithm has to do is you have to determine which of those 3 arrows do you have to follow down the tree. It's very similar to a binary search tree. When you remember binary search, yeah, or a standard binary search on a sorted array, you have to make a decision, do I go left, do I go right? And then you recurse again on that partition, do I go left and right, and so forth. The same for binary search trees. The same for this n-ary tree. You have to make a decision. If you search for, let's say, key 77, where is this? 77. That's, oops. Oh, no, this doesn't work again. Okay. So pen, this is new tools, so the tool doesn't work. So I don't want to done. So I'm looking for 77. Okay. Doesn't write. Okay. Hello? Do you still see it? Yeah, okay. So I'm looking for 77. Yeah, so I will determine, okay, 77 is like in the middle, in between those two values. So I continue by walking down this arrow. Yeah, then again, inside the node, okay, which arrow do I have to follow to find 77? It's again in the middle, in between 73 and 80. So I go down here. Then inside this leaf, I do binary search, and I find out, no, there's no such entry like 77 contained in this tree. Okay? Yeah, so basically run down the tree recursively until you hit a leaf, and inside the leaf you do binary search. So all the data is sorted. So the keys are sorted in the internal nodes, allowing you to do efficiently binary search to determine entries, and the same also holds for the leaves. The data is sorted, allowing you to do efficient binary search. So point query, you simply run down the tree to find those individual entries. Now, if you do a range query, a B tree allows you to do something special that is enabled because in a B tree, you keep extra pointers on the leaf level. As you have pointers, so each leaf has a pointer to its left sibling and its right sibling. Yeah, this leaf has a pointer to the left sibling and the right sibling. So you translate a range query, like from low to high, into a point query to low. Yeah, assume I search for whatever, everything from 77 to, let's say, 100. This is translated by first doing a point query on 77. So like here, 77 is not here. Then I scan through the leaf level until I hit an element that's strictly greater than 100, that's this one. And then I know this range is the range I'm looking for. So it's running down the tree once and then scanning along the leaf level. You could also, of course, do it by, if you want it, you can, if it's 77 to 100, you could also do a point query on 100, this one, and then scan to the left. Same thing, doesn't make a difference. And that's why you have this backward concatenation here. Yeah, is that clear? So there are algorithms that maintain the structure and make sure that the B tree is always in shape. An important thing is what I call a B tree inception. So if you think about that is one tree, right? One tree, one B tree as I defined it with 3 levels. And all of the yellow stuff here is one tree. But if you think about that, you could also view such a tree as one root and its subtrees. Yeah, that is depicted here. So I could say, okay, here's my internal node, which happens to be the root node, and this node points to subtrees. Yeah, I have 3 subtrees here depicted in blue, and what this does is, I mean, it does an interval partitioning at the end of the day. So if the entire tree represents all of the key space, I know, hey, everything here, all the keys in this subtree can only be in this range. They must be smaller 43. Everything that is contained here must be including 43, excluding 91, and everything that's here is 91 including up to plus infinity. That's also how I could regard such a tree. Yeah, it's a root node pointing to subtrees. And if I continue with that, I could also say, yeah, but at the end of the day, I could also depict it like that. I could say, I have my root node that points to subtrees. I don't know how they are organized, but each of those subtrees again are organized like that, saying, okay, there's a root node. So this is an independent B tree, completely independent. Here's another independent B tree, here's another one. Yeah, and they are pointing to the 3rd level subtrees here. Yeah, that's how you could depict such a tree. So basically what I'm saying is those levels are pretty much independent. Yeah? In this example you would say, okay, those leaf levels are valid. Where's my pointer? Oh, come on. So those subtrees are valid B trees. Yeah? So here this is a B tree only consisting of a leaf node, and that is the root node of that B tree. Right? Yeah? So that's how you could regard this structure. So important to understand here is that a B tree recursively partitions the data. Yes, so with each layer you get another partitioning level. That's very important here. Question? No? Okay. Yeah. So the first level partitions it into these 3 ranges here actually, yeah, and the next level partitions it recursively inside that range into those 3 ranges. That is what these B trees are doing. Okay. Yeah, so here a couple of invariants. So what are the invariants of a B tree? The first is each node implicitly creates the horizontal partitioning of the data. That's what we just learned. At all times, the node or leaf is at least half full, if not the root. Those are these roots I depicted before. And the third is the path from the root to any leaf always has the same length. So that's a perfectly balanced structure. And the insert, delete, and whatever operations make sure that the tree is balanced. We won't go into detail in this lecture, more details on that in the core lecture. The entries inside each node and leaf are sorted to allow for binary search. I explained that. Each leaf has pointers to its left and right sibling or subtree, if you want to do this tree inception. Yeah, and then there's this rule 1 saying any insert, update, and delete operation on a B tree must preserve the B tree invariance. Yeah, that's how you read it in the textbook. And there's no rule 2. Yeah, there's no exceptions to this rule. Versus, you will see in practical implementations, there is no such rule 1. Meaning, you will see implementations where some of the invariants are relaxed. Could you stop talking? Whoever is talking, it's really distracting. Thanks. Yeah, so some of the implementations relax some of the textbook invariants. Yeah, for instance, this thing that the root or leaf is at least half full is relaxed here and there to make the implementation simpler. So that's not, strictly speaking then, that's not a textbook B tree anymore, but there are many tricks you can play in real implementations, yeah? Just for you to know if you see real implementations. Okay, yeah, with that, let's look at another notebook. See, that's another way of creating an index, actually. And what I'm doing here is, yeah, I have some geographic data. You can download that from our GitHub repository. That's basically geographic positions of places in Germany. It's publicly available data. So here's a description of that data. So there's a unique ID, there's a name, there's an ASCII name, alternate name, and so forth. That's a description of the schema. And now I want to create an index on that indexes this ID column for whatever reason. So I want to be able to efficiently retrieve certain entries from that data. And I use the file system for that. So basically, this explains the mapping I have in mind. So I want to have a mapping, and that's what the index should support, from this ID to this geographic position, longitude and latitude in Germany. That's what the index should allow me to do. So later on, I will specify an ID, and the index should efficiently retrieve that geographic position. So what I do for that is I basically those are functions that extract the attributes I have in mind. So basically the ASCII name and the position and stuff like that. And then I build the index. And let me just show the example first. Yes, I think I have to do this one. So how it works is as follows. So this is, I use a file system for that. And by that, of course, I also use the I/O services provided by the file system. And what I do is, so the original input file containing all of these entries are now partitioned into separate horizontal partitions. And the convention here is, in this file, I only have entries where the ID starts with a 1. Yeah, so if I open the file, you will see all of these entries start with a 1. Okay? 1, 1, 1, 1, 1. So I horizontally partition using a partitioning function that looks at the first character. These indexes are also called radix, tries, or trees, radix style partitioning. And if you look at whatever other file, all of these entries start with a 7, and so forth and so forth. So that would already allow me to do this trick I explained on the slides. If you look for an ID that starts with 8, you only have to open this file and search within this file. Yeah, you see that in the file, I didn't sort the entries to allow for binary search. I don't do that in that notebook, but it already allows me to reduce the search space for this example dramatically. Yeah? And what I do now is I recurse. So the notebook, if you see the sizes here we have 401 kilobytes, 3 megabytes, 40 kilobytes, and so forth and so forth. So depending on the distribution of those keys in your data, those sizes may vary dramatically. And what I will be doing is, in the notebook, is if the size of a file is bigger than a certain threshold, I will keep on recursively partitioning the file. And of course, I don't partition it then on the first character, but in the second step on the second character, then on the third and the fourth and the fifth and so forth, until each file is smaller than a specific threshold. And you can specify the threshold, of course. So here I'm using, that's this partitioning cutoff. So I'm saying if it's 100 kilobytes, then it's okay. Yeah? Then you stop partitioning. So basically, what I'm doing is I put all of these partitions into a queue, I run over the queue, and as long as there's stuff in the queue, meaning as long as there's a partition in the queue that's bigger than the partitioning cutoff, I need to partition recursively. And that's the output you're seeing here. So the notebook keeps on partitioning recursively. And basically, then you can visualize the tree that is created by that. Now you have to tilt your head by 90 degrees. Basically, you say, okay, this is my folder. So inside the folder, I have certain files that are already small enough. But then there's a subfolder for all keys starting with 6. Yeah, all keys starting with 6 are this file. All keys starting with 6 and 5, and then whatever, and this subdirectory, and so forth, and so forth. So that's basically the tree structure I'm creating here. And of course, you can explore that here. Yeah, and dive into the data. That's weird. No, let's make it smaller. As you want. So again, this is the file 2832. 2832. That's the prefix. That's common. That's the invariant for all of the tuples here in that structure. So that's called a prefix tree. And the interesting thing is, so now I created an external memory structure using the file system. But why did I do it recursively? Why didn't I directly write a file for each prefix, for each key that exists?
Given the condition you mentioned earlier on the size of the file, there's simply no reason to do it by hand. You can just keep going.
Yeah, but what do you mean by keep going? I mean, I do it recursively, like level-wise partitioning, right?
So once you've extracted the number, you produce your search space.
Mm-hmm.
But in this new search space, the problem is invariant.
Mm-hmm.
It's the same problem as before,
Mm-hmm.
so just keep going.
Right, within each subspace I create, it's exactly the same problem. That's the beauty of recursion here. But my question is, we could also read one input file, and for every tuple I find, I directly create the deep folder structure and write it to that specific CSV file. Why not?
Essentially overfitting, right? The depth of the thing you're creating, well, the depth not, but the breadth of the first level will just be whatever amount of data, individual entries you have.
Yeah.
So you're basically, it gives you no information.
Yeah, that's not what I want to go to. So the idea, does someone else have another idea? Why am I doing it like that? Yeah?
If we just traverse the file system for each next digit, we only have at the end one small file, and we have already checked the first 4 digits if we have 4 folders deep.
Mm-hmm.
We just have to read the small file to get the actual data file at the end.
Yes, I guess that's what you meant by overfitting. Yeah, so we will have one tuple in each file. Yeah, but still you could do something in the middle, not create one level one by one, but let's say 5 levels in one shot. Yeah, so you would have a prefix of 5 digits created at the same time. Yes, you imagine that you don't do it on the first digit, but the first 5 digits. Yeah?
It would depend on the distribution of the data, which one would be more fit.
Which one would be more?
Fits to the problem.
Yeah, but what could be? Could you imagine a problem that might occur if you partition directly from one input file into a 5-level tree structure on disk? What could be the problem?
You could basically exclude things which don't have this prefix.
Yeah, sure, but doing the same thing here, because I'm only representing, no?
If you're going one by one, each thing is going to have one of those 9 digits, so you can basically miss anything.
No, but here I'm only showing the folders that exist. You see it here. There's no folder for 4, for instance. So the data doesn't exist. There's no number that starts with a 4 or a 5 or a 0. Yeah, so the stuff is already excluded. Yeah, that doesn't change that problem, yeah?
Will increase the probability that we will have files which are mostly empty.
No, I'm not saying that I will be creating a file for each and every possible prefix. I'm not creating a file for all of the 100,000 possibilities if the prefix has length 5. I'm just saying when I find a tuple, I extract the first 5 digits, and then I check whether I already created a file. Yeah? If not, I will create a new file. If yes, I append it to the existing file. That will be the algorithm that will create the same thing here. I mean, if you can do it in this structure, you can create files in the structure. You'll make one directory with 100,000, at most 100,000 files. Yeah?
Basically, if the data is not static, that's when you get into problems.
Yeah, in both approaches, that's a problem. Yeah.
If you get a new data set for GSM, then you've made no longer holds, then you run into problems with this prefix.
Yeah, that's all true, but it's independent of these two approaches I just explained. So what I'm alluding to is if you partition from one input into many output files, your I/O system will kill you. Yeah, if you create too many files or partition into too many files, like 100,000 times 100,000 files in the worst case, that's not going to be efficient. Yeah, try that on a hard disk. Good luck. Yeah, on an SSD, it's much better. These days on DRAM, it doesn't hurt so much, but for certain storage systems, it's not going to work. And that is why typically you partition recursively. Yeah, you partition from one input file into a number of files that is not too many files in the worst case. And then once you're done, you recurse, as done in this notebook. That is more efficient in general on the storage system, not in all cases, as we have to tweak this number. What is a good number of output files? That's the reason why I'm doing this. Okay, but just to wrap up here, and then you can do the search, and that's basically shown here. Now you can basically navigate along that file structure. So for instance, if you search for this particular key, yeah, so we recurse into the directory structure, look up whether the directory or the file, the CSV exists, and then basically you end up with this 4.csv file that contains, that's here, that's displayed here. So you only have to search in that file to find that entry. Yeah? And if you cat it, you will actually find it, I don't know, boom, here it is. Yeah? That is the entry. Okay, that's what I wanted to show about that one. So I invite you to take a look because this stuff is also very similar to what we asked you to do in an assignment this week. But to wrap up, one final thought about this modeling of costs, because it gets wrong so often. And this slide is not only restricted to cost models, but all models we build as computer scientists. There's this famous quote saying, all models are wrong, but some are useful. Yeah, so a model is always a simplification. You leave stuff away, so a model will be able to predict certain things, but maybe not others. So always keep in mind what the model is built for and what it is good at and what it is bad for. Yeah? So it's important to regularly compare your model and the reality. So for cost models, if you have a predictor on the runtime cost in whatever ways, if you predict the SIO costs, yeah, check back whether that reflects very well what you have in mind. So if maybe you model I/O to predict runtime, is that a good predictor to just look at I/O, yes or no? So you always have to correlate the model with reality. So a model always has a purpose, a certain use. Certain things are simplified or omitted in the model in order to bring out, to focus on other features of the model. Yeah? And that's the essence of abstraction. So that's a thinking process of omitting details and transferring them to something more general or simple. Yeah? So we have all of this reality, all of these confusing things in reality. And what a model does is, well, I have 1,000 features, I will concentrate on these 3 because I believe that those 3 features are enough to predict something. The same stuff is done in machine learning very frequently. Yeah? And the risk is, of course, is that you pick the wrong 3 features, or you omit an important feature, and then your model goes wrong. Yeah? Important is just to make sure you always, whenever you work with a model, don't confuse it with reality. Yeah? It's really 2 things, and I've seen it so often that people confuse that and say, yeah, my model is the same thing as reality. No, it's an abstraction. Come on, man. It's an abstraction. Be careful. Huh? That's all I'm trying to say with this slide. Yeah, so there's some further material if you're interested. So previously, some of the query optimization stuff was done in the core lecture, and there's a recording from a couple of years back, if you're interested, that recaps some of the material, also the stuff we will be doing next week. Well, that's this one. Don't have to watch that if you want. The German book, chapter 8 of Kemper-Eichler, explains the stuff. And there's a very little portion of it in the Masri-Nawate book. However, that's more on database tuning. Still might be interesting to some of you to identify performance problems in a system and get ideas on how to solve those. That's it from my side. See you next week. Thanks.